Hello and welcome to this session on getting started with simulations. So we are just going to have a look at what are the things we need to prepare ourselves with before we start off with simulating a given CFD problem. What we are expecting from you is that you're already familiar with the user interface of ANSYS Fluent and some of the basic terminologies in CFD, the overall methodology, and what you can expect by the end of this lecture is that you can know what you need to prepare yourself with before starting off with the simulation aspects, because often what happens is that users start directly on the software without doing the necessary homework before, and this lecture just helps us to understand what is that work that we need to do before some preparation, and to have some idea about the software before we can start doing a project on it. Just to give you an idea about the presentation, we are going to speak about certain things about ANSYS Fluent, in terms of its dimensions, what kind of problems it can solve, the kind of precision that is involved, and certain features about file handling. We had gone through this in the user interface of ANSYS Fluent lecture, but nevertheless it will be a repetition and maybe a bit more helpful to see exactly how to implement it. We need to be aware of it because sometimes what happens is that we have a lot of data generated, but we don't know how to handle them. So we're just going to see how we can read and write the necessary files so that we can retrieve the data at a later stage, even after the simulation has been done. You'll also see certain features of the mesh, the different units in which we can read in the mesh or scale it, or how we can do some certain modifications, and certain nomenclature of the mesh will also be discussed. We'll also be having a look at some of the features of ANSYS Fluent and some of the options which are available for navigating to the help of the different control panels and some theoretical knowledge of the different options in ANSYS Fluent. So we'll also have a look at the support options. First of all, to start with, we have a look at the launcher, and on the launcher what you have is a choice for the dimension. Either you can choose a two-dimensional problem or a three-dimensional problem. You can define beforehand what kind of mesh you're going to read in, and once we have that dimension defined, we are dealing with the precision of the problem. Now what a precision means is that you're trying to include more locations after the decimal point in all calculations. What it further reflects itself into is that you include more accuracy. But there are problems in which it will not really help to increase the accuracy. It's not really going to serve the purpose. And choosing a double precision solver surely means it's a bit higher computational effort that is required. But this is sometimes necessary in certain class of problems. We're going to look at it in the next slide. Once we choose the necessary dimension and the option, and we say okay, this Fluent session starts. I think you're familiar with this. In the last lecture we discussed about the overall graphical user interface of ANSYS Fluent, and what you can see here at the very top is the dimension. Let's say I had chosen a two-dimensional problem, then this is what comes up here. And had it been a double precision choice, it comes up as 2D DP. Additionally, the next thing that you see here is something about the pressure-based Navier-Stokes equation, PBNS, because the pressure-based option has been chosen. And additionally, it also shows up a laminar viscous treatment of the flow phenomena. So if you had chosen one of the turbulence models, if the flow was indeed turbulent, then in that case, it will be also reflected at the top. Now let's have a look at what exactly this double precision means. So most of the problems we can solve with single precision, but in some cases the geometry has disparate length scales. There are a variety of length scales. There are very small gaps. There are some very big mesh sizes. In such cases, you have a high variety of scales, length scales involved, and maybe also time scales. In such cases, it's a good practice to have a double precision solver. In some cases, it can be that the operating pressure is quite high, but the delta P, the pressure difference which is driving the flow, is quite small. This is another example where it might be very useful to use a double precision solver so that the delta P doesn't get rounded off, the pressure driving the flow doesn't get rounded off If you remember, we discussed this, that this is another source of errors, the round of error done by the computer. So what we are trying to tackle using the double precision is that we are increasing the number of locations after the decimal point. If you are a bit familiar with programming language, I guess you might have heard the term floating point number and double float or double floating point number. So double precision is something like a double float. It increases the number of locations after the decimal point and thereby increases the accuracy of the problem. And there are problems involving conjugate heat transfer, which is another class of problems if there are very varied thermal conductivity values of the fluid and the solid domains that we are having, or if we are having high aspect ratio mesh. Again, it's another example of disparate length scales. In such cases, it's always useful to use the double precision solver, either as a two-dimensional problem or a three-dimensional problem. So just let's get familiar again with the file input output options in ANSYS Fluent. We have already seen this some time ago in the previous lecture. What I had spoken earlier about was the different files that Fluent can handle and can read in or can write. It can import or export. So the typical file that Fluent understands is the .msh file, which is the mesh file. We have the case file and data file. You can read in a case and data file together as well if they have the same names. And in addition, there are some other files located here. The very bottom corner that you see here, these are the history, the files that you had read in the history. Mind you, in connection with the dimension, I would like to mention something here, that in the Fluent launcher, you should have chosen 3D, only then you can read in a 3D mesh. Had it been a 2D choice at the launcher and we launched the 2D session of ANSYS Fluent, in that case a 3D mesh cannot be read in, it will report an error. In that case, please check the dimension of the mesh and the dimension that is mentioned here. So we have seen the slide before about the file formats of ANSYS Fluent. So basically it's an MSH file, .msh file. It's an unstructured mesh file which contains the coordinates of the nodes and the names of the cells. So it's an unstructured mesh. Every mesh element has a name, and this is actually a subset of the case file. Now Fluent, once the mesh has been read into Fluent, what Fluent can further process or write is the case file, which includes the mesh. So mesh file is a subset of case file, and additionally it also includes the problem setup, the numerical and the display settings. And in addition to a case file, a complete problem is defined by its data file in conjugation with the case file. So data file contains the values at the different cell points defined in the mesh of the different dependent variables which have been solved, either initialized or solved through an iterative scheme. So you have all the XYZ velocity values, the pressure values at all the locations which are defined in the case file, in the mesh part of the case file, and all these dependent variables are included within the data file. So case and data file belong together. A data file is unique to a specific case file. It can be, I would more specifically say a data file is unique to a mesh file. So you can have different settings but the same mesh, and you can read in the same data file which corresponds to the mesh, so that the data file knows what are the locations at which these dependent variables that it is storing belong to. So case and data file together will constitute one problem, so that you can do a post-processing, you can retrieve the necessary analytical means or analysis can be performed on the present simulation. So just let's get familiar with different kinds of file compression formats that we have. So typically what we have in as far as the file compression is concerned is that we're having options to read and write files, but in a compressed format, as well as in the normal format without compression. But compression, as I had mentioned in the previous lecture, it reduces the size of the file sometimes by a factor of 2, if not more. So therefore this is very helpful in Fluent. In Windows and Linux operating system, there are different options that we have. In Windows, we can write a file using the .gz extension, and then the file gets written as, let's say, flow.case.gz. It can be any file. It can be also a data file or a profile file, anything that you can write with a .gz extension, and it gets compressed and written down. And in Windows, it's only possible with a .gz extension. Um, but in Linux, you can also use the .z extension, so it also can compress the file in Linux, but Windows cannot do this. Windows can only read a .gz file, so it can be that you're working on one computer which has Linux operating system, and you generate your Fluent session case and data file, and you write them in a .gz extension. Then that can be also read into a Windows operating system if the software is installed on a Windows operating system. But if it had been compressed using the .z extension, then it cannot be read back into a Windows operating system. So just take care about this. In addition to this, Fluent also offers the option that you can write files also having the number of the iteration step, that is percentage %i extension at the end would write the file as, let's say, airfoil minus 005. So this is the fifth iteration step, that's why it has this 005. And in addition, you could have added the .gz extension, which would have compressed the file. In some cases, you can also, if it's an unsteady problem, you can also include the percentage %t extension, which will write the time step. So it's very helpful in data handling here. In addition to this, Fluent also offers the option of automatically writing files. Let's say we leave the simulation overnight and we want to see the results in the morning or after the weekend. Then you can see all the results that would have been saved at a particular frequency, which will be defined by the user. So let's say I define that save the data file every 20 iteration. Let's say the mesh does not change. In that case, you can see you can say use the same mesh file or the case file which you had before, and you just need to write the necessary data files every 20 iterations. And what Fluent offers in the recent versions is that you can also save specific quantities. You don't have to save all the quantities to have a very heavy data file, but you can also reduce the size drastically by just selecting a few quantities. So this is very helpful, especially the additional quantities that you have here. You can choose specific quantities and you can reduce the effort of saving the data file. You need to specify the location of the file name. If you don't specify any location and you just mention the name of the file, let's say the name of the file is curvature tube hybrid initialization or something like this, then it will be saved in the current working directory. So let's have a look at it in a bit more detail. So basically, case and data files, they can be saved automatically, and the interval is something which you specify. It's very helpful if you're doing a time dependent solution, that you want every time step that the solution should be saved, or let's say every 20 time steps the solution should be saved, so that you can do a post processing at a later stage. There is this option of going to this autosave option by going to file write autosave, or in other case you can also just click on this model tree on calculation activities and you can say edit here, and then you can give the necessary inputs. It's very helpful for steady state flows as well as unsteady flows. Let's say steady state flows, I want to save the files at some specific iteration steps. So the iteration number will be added at the end of the file name. In the case of an unsteady flow, it's very helpful to have the time steps written down. So this happens automatically, and you just need to give the necessary interval for this. So this is how it works. So we say how frequently you want the data file to be saved. In case, let's say, I don't want to save all the files every 20 iteration over the whole night or over the whole weekend. In that case, I can say, okay, fine, just save the last 5 files. So in that case, let's say I put in the figure here, retain only the most recent files, and I say 5. Then in that case, it will only save 5 data files at a specific time. So the sixth file which will overwrite the first one. So in this way you can also have a good memory management. And you specify the file path name with the necessary data file frequency, and if the case file is modified, in that case it will be saved, because mind you, for example, if the mesh is getting deformed, in that case it is a case file which is corresponding to a data file. So data file can on its own does not make any sense. The deformed mesh has to be also included. So this is the safest option that I can say, if modified during the calculation or manually. Or otherwise, if you want to save the case file every time just to be on the safer side, then it's also possible. In that case, if I had marked this option, retain only the most recent files, then only 5 set of case and data files will be saved, and at the sixth attempt they will overwrite the first one, and it will continue until you have the last convergence criteria met, or let's say the iteration number of iterations has been met. When it comes to unit systems in Fluent, it's very helpful to know what kind of units Fluent can accept. So Fluent basically can work with inconsistent unit systems. So you can have, let's say, length defined in meters, or and let's say power defined in another unit like watts, which is also SI system, or you can have pressure in bars or in PSI, and you can mix the British and SI unit system or many other unit systems. It's up to you, but basically Fluent at the back end always works with the SI unit system, and therefore it stores also all the results in the SI unit system. So if, let's say, you are trying to customize the software using some user-defined functions through a C programming language, or let's say a journal file or a profile file, whenever you are trying to interact with the source code of Fluent, then you have to be aware of it that all the inputs need to be given in SI unit system. If they are not, then Fluent will take the value that you have specified, which is without a unit. It will take it as the value in SI unit system, and that might be wrong in some cases. So Fluent internally employs some kind of conversion factors, so that whatever input that you're giving in the GUI, that is based on the unit system that you select. So that value is converted using appropriate factors to get it readable for Fluent internally in the SI unit system. So what we have is, if you get to units on the general page of ANSYS session, then in that case such a set units panel opens up, the dialog box in which you can interact with the software, and you can change all units to default. The default contains everything in SI units except for the angle, which is, instead of radians, it's stored in degrees, and it will ask for inputs in degrees. But otherwise you can also select complete SI unit system or complete CGS unit system or British unit system. It's as per your requirement, whatever you are comfortable with. And at any point of time, let's say you want to list all the units of the different variables, the quantities that have been listed down here, then on the terminal emulator you'll be able to see all the different quantities which are being stored and their specific unit system. So this is very helpful to have an idea about what are the units being used. Actually, when you read in the mesh, this is to be noted that Fluent internally understands that the mesh that you have provided to it, even if, let's say, in the pre-processing stage I was operating completely with, let's say, a unit system like Fluent understands the mesh that it has been created in meters unit system. Because Fluent deals with SI unit system, so it understands everything that you provide to it, that it has been created in meters. So let's say I created a room dimension in, let's say, feet, and I want to read the mesh into Fluent. Once I'm in Fluent, I can do a scaling. I can say, yes, the necessary dimensions that are there were created in a specific unit system, and I can select that unit system. And what you can see here is you can specify your own scaling factors by which you want to scale down or scale up your mesh, or you can choose that, okay, you can say, okay, all my dimensions of my, let's say, a nozzle were created in so I can say and in that case Fluent will automatically scale down the mesh by a factor of 10 to the power of 3, and it will treat then everything to be consistent in the SI unit system. What this panel also helps to get to the scale, mesh scale, if you get there, what you can also see here is the domain extent. And now that's very helpful, that you can see here the extent of the domain. Let's say I have an idea about how big the domain is, and from this I can conclude, okay, this nozzle is not really of such a big length as, let's say, 70 centimeters, as in this case, along the x direction. So it has to be scaled down by a factor of 10, let's say, to get it into or something like this. So such kind of operations can be performed, and this is very helpful to do this at the Fluent stage instead of scaling it down at the pre-processing stage. Now, what additionally we can do as far as the unit systems are concerned is that you can also create your own unit system in some cases. So what's helpful is to define your own unit system. You can say click on just new after having selected a specific quantity. So I select time and I say new, and I define a new unit called hour, and I say that this hour is 3600 times the SI unit system which is included within ANSYS code. So I will say hour is 3600 times seconds. So that's a perfect understanding of the unit hour. Similarly, you can also give an offset in some cases, especially let's say you are shifting over to a temperature unit, which converts Kelvin into a specific factor and also includes an offset, as it is in the case of degree Celsius or Rankine. Then you can also include those things. You can access more how to deal with this unit system by just clicking on help, and an appropriate window opens up to explain to you what and uh, in which way you can give the necessary inputs to define your own unit system. Let's come down to mesh modifications in ANSYS Fluent now. We are going to have a look at how you can modify your mesh, not just scaling, but you can do certain more features, and we'll have a look at them. Once the mesh has been imported, one of the important things that you can do is you can modify the grid by either translating it or scaling it. As we've already seen about scaling, we'll also have a look at translation of the mesh. You can also partition your mesh for parallel processing. You can reorder the mesh. This is a typical thing that we often do. What it does is it decreases the bandwidth. Um, as a user, what you can understand from this is that overall the memory efficiency becomes better, and overall the calculation process can become quite quick in that case. You can also merge or separate zones. Now that's very helpful. Let's say we are having a collection of inlets. We want to give the same boundary condition in all the inlets. Then in that case we can call all of them by one single name. So you can merge the different inlets by a single name, or you can also separate. Let's say there are many candidates in a room who have been meshed, or their body surfaces have been meshed, but I want to give different heat inputs to the different persons in the room to do an analysis of heat, ventilation and air conditioning. In that case, you can also separate the different mesh zones on different bases. Such things usually are helpful to be done already at the pre-processing stage, but there are certain options available also in Fluent to do. You can also adapt your mesh according to the solution, and we can also diagnose the mesh based on the memory usage, certain features like the number of faces and cells, and the different zones which are there. I'll speak about zones in a few minutes from now, but you can also see what is the characteristic, what are the quality criteria of the mesh, how big and how small the mesh is. So usually we do this by checking the mesh. Once we are done with having an idea about what are the different kinds of possibilities that by which we can do some mesh modifications, we can also have a look at how the grid is understood by Fluent. So Fluent can basically accept any kind of unstructured mesh element. It can be a hexahedral, tetrahedral in 3D, or it can be a prism or pyramid as well in 3D. In 2D, it can have triangles and quadrilaterals, and what it can also do, since the 6.3 release, in all the subsequent releases, Fluent can also accept polyhedral mesh, either in 2D as a polygon or in 3D as a polyhedral element. In addition to this, Fluent can also have a hybrid mesh, a collection of tetrahedron and pyramids and prisms and hexahedral elements as well. So it can have a combination of different mesh types. This is no problem for Fluent to solve problems on such a collection of mesh elements. What additionally Fluent can handle, it's a very strong feature of Fluent, is to deal with non-conformal mesh. I'm going to speak about more in detail, but one kind of non-conformal mesh that you can see here is a hanging node. Now this is usually generated when you're using the Cartesian mesh generator. So you get a trimmed mesh. That's the terminology of CD Adapco for its product Star CCM Plus. So you can also generate such trimmed mesh or such a Cartesian mesh in which you can have one big let's say a square divided into four smaller squares. So in this way what you end up having is one mesh element in which a node is hanging from the previous set of elements, which is shared by the previous set of elements, and this is a hanging node example. Usually it does not include a huge amount of error into the solution, unlike the other non-conformal mesh, but such kind of hanging nodes can also be handled by ANSYS Fluent. ANSYS CFX is incapable to deal with hanging nodes, just that it is known to us. But software packages like Fluent or STCM Plus, Star CCM Plus can handle such hanging nodes as well.